everyone, my name is Aisyah Syafinaz Suarin. I am from Faculty of Electrical and Electronic Engineering, Universiti Tun Hussein on Malaysia. Today, I am gladly to present and share with all of you our research paper with title Stingless Bee Honey Classification using Near-Infrared Light coupled with Artificial Neural Network. The authors of this paper are me, myself with Fathen Nasohah and Dr. Chia Seng, and here I am as the presenter. Without further ado, I will start now. There are two types of raw honey, which are wild raw honey and farm raw honey. Wild honey is produced in the natural beehives of the cliffs and trees in the forest, while farm honey is the honey that is produced in bee boxes by beekeepers. Even though both farm and wild raw honeys are better than processed honey in terms of nutritional value, wild honey is more expensive than farm honey due to its scarcity, nutrition, and quality. According to International Honey Commission, the sweet substances produced by honeybee from the nectar of blossom or from secretion on living plants, which the bees collect, transform, and store in honeycombs. Honey is superfood, contains glucose, fructose, and water, in addition to small quantities of proteins, mineral, organic acid, and vitamins. Raw honey has a high antioxidant level and possesses various biological activities such as antibacterial agent and anti-inflammatory. Recently, the seriousness of fake honey and adulterated honey has become a huge issue as reported by many local and international newspapers and articles. In 2012, there was 65% of fake honey in market, and in 2017, the number has increased tremendously by 15% and become 18%. Among various technologies available nowadays, near-infrared spectroscopy technique has been widely evaluated to replace time-consuming, costly, or destructive conventional measurement approach in various fields. This technique can determine honey component as well as food authentication. Although near-infrared spectroscopy is promising to assist consumers to differentiate types of honeys, the financial barrier to have a near-infrared spectroscopy is needed to be addressed. Thus, this research aims to evaluate the performance of a low-cost near-infrared light acquisition alternative that was developed in classifying stingless bee honeys using artificial neural network. Lambert's law is one of the laws that related to spectroscopy theory. As stated in equation here, the optical path length traveled by light spectrum through the sample is proportional to the absorbance value, where A is the absorbance value, I naught is initial light intensity, I is the intensity of light after the light has passed through the sample, epsilon is molar absorption coefficient, C is concentration solution, and L is the optical path length. And this is the research flow chart. First, stingless bee raw honey samples, 164 samples were prepared, which comes from farm and wild honey. Next, data acquisition process. The experiment was run by using the setup device. After that, the collected samples with their corresponding classes were divided to training, validation, and testing samples. All the samples are also grouped into different datasets based on distance from light sources to light sensors. Next, the stingless honey dataset were trained by artificial neural network classification model for different number of hidden neurons. Lastly, the results were recorded and analyzed to conclude the findings. Figure here shows diagram of the proposed circuit for spectral data measurement device that consists of 4 infrared photodetector amplifier, 5 near-infrared LEDs with different wavelengths as well as Arduino Uno as microcontroller. The 4 near-infrared LED with different wavelengths are 850 nanometer, 860 nanometer, 870 nanometer, 890 nanometer, and 910 nanometer. LED were used to emit near-infrared energy. To prevent external light disturb the experiment, the circuit was placed in the non-reflected black box. Artificial neural network learning algorithm was applied to analyze and develop classification model for differentiate type of raw honey. The architecture is as shown in figure here. There are 5 inputs, which are the near-infrared LED with 5 different wavelengths, two outputs, which are class 1 for wild stingless bee raw honey and class 2 for farm stingless bee raw honey. The artificial neural network model developed was single-layer, sigmoid learning for activation function, trained with scale conjugate gradient backpropagation algorithm, and the number of hidden neurons was investigated from 1 to 10 number of hidden neurons. The performance of model developed by ANN was evaluated in percentage of true positive classification and cross entropy value. And here is the equation and how we can evaluate the true positive and cross entropy value. Now let's proceed with result and discussion. We will discuss about the first finding, which is the hidden neuron analysis. Figure here shows the combination graph of true positive and cross entropy value, which is summarizing the performance of classification model developed by artificial neural network for different number of hidden neurons. By analyzing the result of training, validating, and testing true positive and cross entropy value, 8 number of hidden neurons show the best performance with the highest percentage of true positive percentage with 96% and second lowest value of cross entropy 1.13. There is no trend to conclude the relationship of performance of TP and CE value with number of hidden neurons. This is because there are more parameters need to be controlled, for example, weightage, bias, and learning rate. However, selecting low number of hidden neurons is suggested to avoid the increase of complexity of the model. As shown here, the architecture of artificial neural network, the hidden layer is where the neurons place. If the number of hidden neurons increase, the complexity of the architecture will be increased and will affect the model developed. Our second main finding is the performance of classification model based on different distance of light source with light sensor. Table here tabulated the result of true positive and cross entropy for 6 different datasets. The datasets are different in terms of distance of light source with light sensor. The best results shown by dataset F with the highest testing percentage accuracy of true positive, 96%, and among the low cross entropy value 1.14. Dataset F consists of data acquired by the farthest placement of light source and light sensor with an average distance of 40 mm. The result indicates that distance between light source and light sensor is important to produce good classification model of different type of stingless bee raw honey. Intensity of light source emitted on the sample and received by the light sensor might be saturated to be measured if the distance is too close between components. This is shown by the result obtained by dataset E, which is the worst performance of classification model with true positive accuracy percentage 56%. Dataset E consists of light source and light sensor with the closest distance between each other. If the distance too far, it might cause the light to be dispersed to the environment before passed through the sample. Thus, maintaining appropriate distance between light sensor and fixed intensity of light source is important. As a conclusion, this study evaluated the performance of a low-cost near-infrared light acquisition alternative in classifying stingless bee raw honeys using artificial neural network. Results indicate that near-infrared light coupled with artificial neural network by using 8 hidden neurons and an average distance of 40 mm from light source to light sensor was able to achieve the best result with the best true positive correct classification percentage accuracy and cross entropy value of 96% and 1.14 respectively. This finding suggests that the proposed alternative is promising to be further developed for consumers to differentiate farm and wild stingless bee honey that can safeguard consumers' interest in honey purchase. For future work, our planning is to develop a portable in-situ stingless bee raw honey classification device, which is a consumer-friendly device with good performance and high accuracy. This is the question and answer. This is the question that we received from TPC. I think I saw a device using some kind of RGB sensor or spectroscopy to assess the nutritional value of the food it is pointed to. Although the device might have been naive, how far are we from actual consumerization of automatic food composition detection? TPC. Okay. For our research, we have completed the technology readiness level 1 to 3, which is the basic research as that presented in this paper. Our next research milestone will complete the technology readiness level 4 to 6, which are the proof of concept via scaling up the research and evaluating the robustness of the solution. From my personal point of view, I will say we are close enough for automatic food composition detection. With the rapidly growth of spectroscopy technology in design and research, and with the progressive contribution of artificial intelligence to our technology, these two will play their role really soon and perform in automatic food composition detection. That's all from me. Thank you.